we've seen linear inequalities, and really those are linear inequalities with one variable that are solved like linear equations. But now I want to look at linear inequalities in two variables. And what I mean by that is that they have this form: ax plus by, some sort of inequality symbol c. So in this case I used less than c. Now of course that could be greater than c, greater than equal to, etc. Okay, and so the way to think about this is we know what ax plus by equals c is. That's the equation of a line. That's the standard form of the equation of a line. So if you see my picture here, I have an axis with a line represented by this dotted line, and it says ax plus by equals c. That is the dotted line there. Now where the inequality comes into play is if I had ax plus by equals c, then any point that's on that line is a solution to that equation. But if I want less than c, then I don't want the points actually on the line. What I'm looking at now are the points that when I plug them into this equation, I get something smaller than c. And so that generates a half plane, right? We cut the xy plane into two big parts. And this part that's shaded blue now is the part that satisfies this inequality. Okay, now I'm going to show you several examples of this, several examples of how to solve these things. There's a process to follow. We'll follow this process, and I think it'll make sense. Alright, so step one in this process is, like I did here, is first you graph the line replacing the inequality with an equal sign. Alright, so in this case it would have been ax plus by equals c. You graph that line first. Secondly, depending on if I have less than or equal to, or greater than equal to, if I have an equal to part, I make this line a solid line. If it's not equal to, like in this example, it's a dotted line. So if I had changed this to say less than or equal to c, now all of a sudden I want a solid line instead of a dotted line. The reason being is the dotted line implies that the points on that line are not included in my answer, whereas the solid line means that those points are now included in my answer as well. And then step three is determine which part of the plane do I shade. Do I shade the top part like up here, or do I shade the blue part like I did? And so you can do that by figuring out a test point. You just pick a point somewhere out here, plug it in, and see if you get a value less than c. Alright, so let's look at some examples, and hopefully this will make sense. Okay, so here's my examples. I want to solve these inequalities by graphing. In part A, I have x minus y is less than or equal to 0. What this means is that we're looking for all the points x and y, such if I say x minus y, I get 0 or less. So let's follow our process. The first says, step one is to graph with just equals. So I want to graph y minus x equals 0. Okay, so first of all, let's figure out what does that look like. Let's get in a form that we recognize. So if I subtract the x over, I end up with y equals x. Okay, so that line, this is slope-intercept form, right? I have an intercept of 0, and I have a slope here of 1. So that means I go to the right 1, to the up 1 to get my second point, and there I put it connected like that. Okay, now step 2 says to determine if it's a bold or a dotted line depending on the equality symbol. Since this is less than or equal to, I'm going to get a solid line here. Now all I need to figure out is which side of this do I need to highlight? Which side is the colored region? Okay, so what I'm going to do is pick a test point. So if I pick something down here in quadrant 4, that means I go positive in the x direction, negative in the y. How about something like this? 1, negative 2. Let's plug that in. I get 1 minus a negative 2. What does that become? That becomes a positive 3. Which is not less than or equal to 0. Okay, so that means that this is not part of my region, and this other part is. Okay, so this is actually the part we want to highlight. You see why the test point's useful, because at first it's tempting to say, since it's less than or equal to, I need to highlight the bottom part, but actually it was the opposite. It was the other direction. Alright, so let's look at part B. So this time I have x minus 3y is greater than 6. So we're going to do a similar thing. First I need to get in a form we recognize. So let's see, that's negative 3y equals negative x plus 6. So the y equals, dividing by negative 3, I get a positive 1/3 x minus a 6 over 3, which is 2. Okay, so now I can graph that line. I have a y-intercept this time at -2 and a slope of 3. So that means I go up 1 to the right, a slope of 1/3. So I go up 1 to the right 3. There's my second point. All right, now before I connect, let's think part 2. Since this is a strictly greater than symbol, I'm going to put a dotted line across here. So that means that the points on the boundary here on this line are not included in the answer. And now I just need to figure out which part to highlight. Okay, so I'm going to pick something, how about in the second quadrant? That means I have to go negative in the x direction and positive in the y. So let's say, how about -1, +3? That puts me up there. Plug it in, let's see what we get. So we get -1 minus 3 times 3, which is 9. So that ends up being -10. That is not greater than 6. Okay, so that means that region is not the correct region. Actually, down here is. So this is the correct half plane that I need. And any point down here satisfies this inequality. All right, let's look at one more. All right, so this time we have x is less than -4. Okay, so as a line, I'm thinking x equals -4. Oh, that is a vertical line. All right, so when I graph it, here I'm at -4, and this is strictly less than, so it's a straight dotted line right at -4. Okay, now I'm trying to think what side is less than -4. Well, I think we could see that it's going to be this side. And if you don't believe me, just pick something over here. Okay, so here maybe this is like -5, 10, something like that. -5 is less than -4. This is the right half plane. I'm going to show you a couple more examples of a few things that are a little bit more complicated, but it follows the same principles. Alright, so this time, in example 2, I want to graph the following inequalities. A says y is less than or equal to -6x minus 9, and, that's kind of a curious expression, that's something we're going to need to keep up with, y is greater than or equal to -2x minus 5. So now what I need to do here is I need to graph both of these lines, or both these situations, and then let's see what the and has to say about this. Okay, alright, let's figure these out. Okay, so here I have my axis. The first one, part 1, I'll do in the light blue, has a y-intercept of -9 and a slope of -6. Okay, so I don't want to go down and to the right, so what I'm going to do is I'm going to go up 6 and to the left 1. And this is the point if you want to think about it. So I went up 6, so my y-coordinate is -3 now, and I went to the left 1, so it's -1, -3 at that point. Alright, and so there's my line, and it is a solid line. And if I want to figure out what side of the plane to graph, okay, I can plug in a test point. If I plug in something in the first quadrant, 1, 1 for example, and I plug it in, I get 1 less than or equal to -6 minus 9, and that is not true. Okay, so I'm going to graph, I need to shade in this part of the plane. Okay, so there's my first one. The second one, which I'm going to do in this nice vivid green here, says we have -2x minus 5, so I have a intercept at -5, something like that, and a slope of -2. So I go up 2 and I intersect actually at this -1, -3. Alright, so now when I graph this, I have a solid line again because it's or equal to, and I just need to figure out which side to highlight. So let's try 1, 1 again. If I plug in 1, 1, I get 1 is greater than or equal to -2 times 1 minus 5. That's a true statement. Okay, so we graph these two things on top of each other. What does this have to do with an answer? Well, that's where the and comes into play. And so when you see and in mathematics, that means something important. It means both things are true at the same time. So in other words, I need to figure out where this happens and this happens. Where do they both happen? And so if you notice, this little triangle wedge area here, which is actually extended out infinitely long in this direction, that is the region that is both purple and blue. That is the and solution to this inequality. So let's look at part B. And now notice this time I have an or situation. So I'm going to graph these two lines quickly because we've been through this several times now. I'll graph the first in blue and the second in green, okay? And then we'll discuss the or. Okay, so I did a lot of work here really quickly. So if you notice, this blue line here isn't dotted because it's a greater than, and the purple is shading the correct region there. And then for the green line, the blue is shading the correct region there. Okay, so now how does OR come into play? Now, AND meant both things have to be true at the same time. OR in mathematics means only one of them has to be true. Okay, so anything that satisfies either one of them works. Like if your friend said, oh, I could go to McDonald's or Subway, that means that they're fine with either one. Okay? But they said, I need to go to a place that has cheeseburgers and fries. Okay, that means you need to find a place that satisfies both of those. Alright, so for this example, the OR then would actually be everything we've done. Okay, so all this shape here and beyond what we've drawn, all this is included in the OR. Okay, because all that region satisfies one of the two inequalities. Alright, now I'm going to show you one more example that kind of ties this together. Okay, so this time I have an absolute value, x minus 3 is less than or equal to 1. Okay, so now when you have absolute value situations, to drop that, if you remember, means that you have to consider both cases. This means less than or equal to 1. And it also means greater than or equal to negative 1. And it has to meet those simultaneously. So this is an AND situation. Okay? So here we graph these lines just like we normally would. And they're both vertical. So this first one ends up being x less than or equal to 4. This one ends up x is greater than or equal to 2. Okay? So here we have 4. And I'm talking about this region. And on the other hand, we have 2. And I'm talking about the region greater than that. So you can see the AND would be this column here in the middle, in between the two. And any point in there satisfies this absolute value inequality. Now in the other case, let me show you quickly. If you had said this, x minus 3 is greater than or equal to 1, okay, that means that you're going to flip both inequalities here, here, and here. And in doing so, you're also considering an OR situation. So an absolute value, if your absolute value is greater than or equal to something, you have an OR. If it's less than something, you have an AND. So in that case, you can imagine it had been like out here for the first one, and out here for the second one. And so the OR situation would have been all of this. That would have been the OR situation if we had had this equation. Okay, so I've thrown a lot here. I've thrown a lot at you. I hope this makes sense. If you have any questions on it, please let me know. If you're confused about the absolute value inequality, I have a video covering absolute value inequalities that hopefully will help clarify this. If you're curious about this more, you should look up linear programming, and businesses use this in applied ways to find interesting results and maximize profit. If you have any questions on it, again, please let me know. I'd be glad to help, and thanks for watching.